Okay, the next talk of the session is by Paul Valiant. It's on mean estimation in low and high dimensions.
Okay. Yes, great. Okay, so I'm very happy to be here. The talks so far have been great. I'll try and live up to that. The questions so far in the talks have also been great. It's up to you guys to live up to that. Mean estimation in low and high dimensions. I've been working on related problems for a while. There's tons of things I want to tell you about, not all of which may fit in 25 minutes, but I'll say something. So this is based on joint work with Jasper Lee, who was my grad student at Brown. He's a postdoc in Wisconsin right now, and I expect will be on the job market soon, so look out for him. Okay, so mean estimation. Given data from, say, some underlying distribution, how do we estimate the mean of the underlying distribution? So this shows up in real-world situations. So you've got, say, a complicated physics experiment that's generating samples, say, just for the moment, real-valued samples from some distribution. So these are drawn, displayed left to right on some histogram, where we get like three things, samples from the middle and some certain distribution like this. And how do we reason about the underlying physical process? So mean estimation is both one of the most important data primitives in practice. It's also a subcomponent of almost anything else you want to do, like maximum likelihood estimation and regression, all can be viewed as having mean estimation as their way of accessing the data. Mean estimation is also, of course, a subcomponent in many theoretical algorithms that use mean estimation in the middle of a Chernoff bound or something like that. So this is a really basic problem. So the natural thing you want to do is, your first instinct is to return maybe the sample mean. So given some data like this, if you want to estimate what's the mean of the true process, you can just return the mean of what you've observed so far, which is depicted by the yellow arrow. And in many cases, this works really well. So if your distribution is Gaussian or something well-behaved, then the sample mean will look great. But okay, so we've collected some data. What if the next data point we get is way out far to the right? What do? Suddenly we have a problem. Before this data point arrived, just returning the sample mean, we could sleep well at night if we did that. Now suddenly something ridiculous happens. Well, okay, I mean, maybe it's an outlier, maybe it's not important, maybe we got unlucky with our sampling process. But I mean, what if we get two data points from out there? So at some level, the mean estimation problem boils down to issues about how do you actually deal with outliers? Do you take them seriously? Do you throw them out? What's the optimal thing to do with this? Okay, so currently we have 10 data points, and 2 out of 10 of them are outliers. So what does this mean? So 2 out of our 10 data points are outliers. This is compatible with a universe where the true probability of this outlier is, say, 1/10, or observing it 2 out of 10 times compatible with the true probability being as high as maybe 4 out of 10. So in some sense, what we're trying to reason about is what's the most extreme distribution that could have led to the observed data. And then we return a mean estimate that's sufficiently accurate for all the possibilities that could have led to the data we observed. However, even if we see 2 out of our 10 data points being here, there's still some chance that actually something really weird happened. So if the true probability of this data point far to the right is 0.0001, we still could have seen it 2 out of 10 times with probably 1 in a million. So how robust do we want our estimate to be? If we want to be robust even up to 1 in a million probability events, then we need to take this possible universe that could have led to our data into account. So the optimal algorithm must depend on the desired confidence. Okay? Okay, so the overall goal, so given n samples from some unknown distribution p, we want to return a mean estimate that's accurate to plus or minus epsilon, and that succeeds with probably 1 minus delta over the randomness of the sampling process. So the question is, what's the optimal trade-off between the number of samples, the accuracy, and the desired confidence? Okay, so for any distribution, we can ask this question. Computation time is not one of these 3 things. As it turns out, the algorithms we're going to talk about today are all linear times, as fast as you could hope. But in other cases, it's there's more of a balance between these 4 factors. So today I'm going to tell you about the low-dimensional case and a high-dimensional case. So first part of this talk is about the 1-dimensional mean estimation case. Last part of this talk is about a very high-dimensional case. And this ties in with a new vector Bernstein inequality, which is a structural result, which I'll tell you about later, and which I think you might find interesting. It's pretty general. So just to give some extremely high-level perspective, so we hear about algorithms and lower bounds. Yeah, question. Yes. Okay, so the question was the trade-off between n, epsilon, and delta. Is this a worst case bound or something else? So yeah, the results I'm going to talk about today are worst case parameterized by the variance of the distribution or covariance of the distribution. But in the open questions slide, which you've anticipated, you can of course ask about more instance optimal style bounds, and this is a very tempting direction to go in. Okay, so just to give some extremely high level perspective, there's tension between algorithms and lower bounds. And we often pair these up with the words efficiency and complexity. And so, time efficiency versus time complexity, space efficiency versus space complexity. And the word that the phrase which I've been using this for about 10 years, and I want you guys to start using this too. I don't hear this that often. Data efficiency versus data complexity. So I just want to say immediately that for the purpose of this talk, this is essentially the same thing as sample efficiency and sample complexity. But data is kind of a more general phenomenon. Where does your data come from? It's not always coming from a sampling process. So I'm trying to draw attention to the fact that, when if you've got some real world problem, is the limiting factor computation time or computation memory? No, often the limiting factor is data. We're in this big data era where for many companies, their data is the most valuable thing they have, and they're limited by data. These questions of data efficiency and data complexity are kind of the driving factors that drive many companies' business. So even though for this talk, it means the same thing as sample complexity and sample efficiency, I'm going to use the word data complexity and data efficiency just because I want these words to catch on. I think it captures a more general phenomenon. Okay, so we want to estimate the mean, find the optimal trade-off between the number of samples, the accuracy, and the confidence. Okay, so what's our goal here? So let's benchmark against the ideal case when things work really well. So if the underlying distribution is a Gaussian, then the provably optimal thing to do is return the sample mean. So how well does this do? And we will benchmark ourselves against a Gaussian, but for an arbitrary distribution. Okay, so given n samples from a Gaussian variance sigma squared, how well does the sample mean perform? So you can work this out. It does roughly what you'd expect. So with confidence delta, the answer will be accurate to plus or minus the standard deviation times square root of 2. There's a log of the confidence factor, and you divide by n. Okay, so these parameters are all roughly where you would expect them to be. So now the question is, what if we have an unknown distribution of unknown variance? Can we get an algorithm that will approach this performance, approach this ideal case, but for any distribution? Okay. Okay, question. And yes, the answer is yes. So the theorem is we can actually do this, even down to the 1 plus log of 1 factor. Okay, so to motivate this, let me try and describe somewhat quickly the entire history of mean estimation up till this. So sample mean. Why isn't this good enough? The sample mean works great for Gaussians, but okay, so supposing we take n samples from some distribution, and supposing this distribution is very uneven. So there's, sorry, can I? I can use some math, okay. So there's a big probability of generating 0 and a tiny probability of generating some other thing, which I'm calling 1, but think of it as being some huge number. So the mean of this distribution is 1 over 1000n. And what happens if we take n samples from it? So 99.9% of the time, all of the samples will be 0. And our sample mean will be 0, which is actually pretty close to the actual mean. However, 0.1% of the time, we will see one of the rare elements, and the sample mean suddenly jumps up to 1 over n, which is 999 times as big error as the typical case. So the sample mean is unbiased, but it's not robust, in that here, 1 out of 1,000 times, this error is basically 1,000 times as big. This is not a robust behavior for this algorithm. And this is basically the issue, that if we want an answer that's accurate even 99.9% of the time, the mean estimate actually has huge error if we really insist on a small delta. Okay? Much more sophisticated and robust answer is median of means, which for many purposes is the only answer you'll ever need. So the median of means algorithm is extremely simple. The analysis I won't have time to explain, but it's really nice, very clean. So take your data, split it into roughly log 1 over delta, where again, delta is your desired confidence. Split your data into log 1 over delta groups. Just split it just in, it's obliviously, just without looking at the data. Compute the mean of each group and compute the median of the log 1 over delta group means. So the intuitions at some high level is that the median is robust. Meanwhile, each sample mean of the groups is unbiased. So taking the median of all these nice unbiased things is going to somehow get the best of both worlds, both the robustness and accuracy. And the error of this algorithm is this expression here. And if you remember from the Gaussian slide, this is exactly what we want, except for the factor of 20. For Gaussians, the number is 2. Here, the number is around 20, depending on how you analyze things. And this is what this work is about, trying to reduce 20 to a 2. Do we care about constant factors? Well, the answer is sometimes. People have argued that for computation speed, constant factors don't matter that much. But I'd argue that for data efficiency, often constant factors are crucial because maybe you can get an extra factor of 2 CPU time if you just rent a bigger cloud instance or whatever. But your data is your data. Sometimes you just can't get twice as much data. So what's the best you can do with the data you have? So these constant factors in data efficiency, I think, matter sometimes. Okay, so this is great, except it uses a constant factor more data than we might like. What can we do? Okay, so jumping forward again. So this paper by Catoni, in some sense, revitalized interest in this area, or I guess spurred the modern interest in this question of mean estimation. To explain his algorithm, just as a warm-up, so we've been looking at mean and recently median of means. So I'm going to re-express these in different terms. So given data, one way of expressing the mean is as the point minimizing the sum of the squared distances from you, the point u that has minimum sum squared distances from your data. Taking the derivative of this, it's and setting it equal to 0, this is a point such that the sum of the data point minus u equals 0. You can also express the median in this way. The median is a point that minimizes the sum of the absolute differences to u, the minimum L1 distance instead of L2 distance. And taking the derivative of this, the median is a point such that the sum of the signs of data points minus u equals 0. Okay, so this is the mean, this is the median. And trying to get the best of both worlds, trying to really blend mean and median, well, one way of doing this is to define some function psi that is somewhat a blend between the linear function and a sine function, and solve this equation for that. Okay, so this will come up with some estimator that's somewhere in between the mean and the median. So we pick some function psi that is linear near 0, so it behaves like the mean for small data, but for big data it becomes more median-like, it becomes more robust. So pick a function like this and solve for, and then solve for the u such that psi of x minus mu, u equals 0, okay? This is a general prescription. So Catoni picked a particular function. The details won't matter, but particular function that behaves like this close to 0 and constant away from 0 with odd symmetry around 0. So this is some function like this, okay? So one really high level thing I want to point out, these influence functions are super nice for analysis because suddenly the equation we're solving is an IID sum. Like each data point xi contributes independently to this, so we can suddenly use Chernoff bounds. So one way of transforming a really hard to analyze algorithm into an easy to analyze algorithm is to transform it into something, an implicit algorithm in terms of these psi functions. Then suddenly you can use things like Chernoff bounds. So this is a really powerful technique. Okay, so this is Catoni's algorithm. It works great. There's one issue with it. So again, the error here is exactly what we want. The one weird thing with this algorithm is that 1 over sigma appears in the definition of the algorithm. Okay, so sigma is, of course, the standard deviation of the distribution. So this is a weird kind of cheat. So we can estimate the mean really well, assuming we already know the standard deviation. Okay? Like we're assuming we know the L2 norm of the distribution and we're using it to estimate the L1 norm. This is a little bit weird because higher order norms are often harder to estimate. So yeah, sorry, I realize you can't see the red. So the theorem is that if you know the variance, or if it has well enough behaved higher order moments that you can estimate the variance from the data, then you get exactly what we want. But this doesn't work unless you can do this. Okay, so the challenge, this needs to know the width of the distribution. Can we succeed without this? Yeah.
So are we still in one-dimensional case, or does this generalize to multiple higher dimensions?
Yes, so the high-dimensional case is very different. Yeah,
These are all for one dimension.
Yeah. Even defining the median in high dimensions is very weird. There's many ways to define the median in high dimensions. They all work differently. They're all complicated. Most of them don't work. Don't work for this. Okay, so let me just briefly explain the algorithmic idea here, and then I'll talk a little bit in the next few minutes about the higher dimensional case. So I want to give you some algorithmic intuition for what to do here. And to do this, I want to talk about the simplest instance of this problem. Just results from a coin flip. So supposing we flip a coin n times, we're going to see k heads and n minus k tails, like k ones and n minus k zeros. And the question is, what do we do? So our algorithm has very few inputs. It knows what k is. It knows delta, the desired confidence, and it, of course, knows the total number of coin flips. So given these numbers, what do you return as the mean estimate? There's just so few ingredients on the table that, trying to find the optimal thing, like there just isn't that much you can do. So given k and delta and n, what do you do? Of course, the sample mean is just k over n. Yeah. So given k, so k over n is the natural thing to do. Can we use delta to do anything more clever than this? Okay, so to present a diagram, so given a coin that's got bias p, I just want to plot its probability. and I'll plot it on a log axis, the probability of various different outcomes. So the most likely thing to happen is that we get n times p heads, yeah? And roughly, things will look sort of quadratic beneath this. So I just drew a quadratic function beneath this. So if we had like a Gaussian distribution, then the log probability would in fact be quadratic. We don't have a Gaussian, we have a binomial distribution, or roughly a Poisson distribution. And the crucial point I want to make is that a Poisson distribution is skewed a tiny bit compared to a quadratic. Okay? Exactly how is it skewed? Well, we care about the delta unlikely events. So if you draw a little line around delta probability, the question is, what is the skewness? What is the offset between the actual probability here, like where the actual probability intersects this delta unlikeliness, versus the symmetric case? And sort of weirdly, independent of everything else, the skew is a third log 1 over delta. It doesn't depend on p, okay, up to first order. And so when we observe the number of heads, the number of ones, instead of it coming from an interval centered at NP, it'll come from an interval offset from this by a third log delta. So it turns out the optimal thing to do, the most robust thing to do, is when you get your observations, subtract a third log delta and then return the sample mean. So instead of returning k over n, take k, subtract a third log delta from it, and then divide by n. So this is the way to debias the inherent skew in any kind of process like this Poisson process. Yeah. Okay, so here's the algorithm for one dimension. And then after this, I'll switch to just briefly talking about the high dimensional case. Throw out a third log delta of the most extreme elements and return the mean of what remains. So this needs to be fleshed out a little bit. So you throw out the most extreme elements centered where? Well, use some mean estimate, like the median and means algorithm, to find some rough center, and then throw out things far away from that. How do we throw out third log delta elements? Well, throw them out in a slightly weighted manner. So you throw out maybe all of the really far away elements and throw out half of some closer in elements. What are the weights? Well, the weights will be proportional to how far away you are from the center. How do you pick the proportionality constant alpha? The weights will be proportional to how far away you are from the center, though don't throw out more than one when you get a sample, don't throw out more than the entire sample. And how do you pick alpha, the proportionality constant? Well, pick it so that you throw out a third log delta total elements. Okay, so there's a lot of very delicate choices here that I can't justify, but you can perhaps appreciate that this is trying to achieve this intuition of throwing out a third log delta of the most extreme elements. So once we understand what to do with this really classic case of unfair coin flips, then generalizing this is, I think, reasonably intuitive. So this is the algorithm. It looks very different from Catoni's algorithm. It doesn't require, of course, any a priori knowledge of the width of the distribution, but it emulates what Catoni does, except without, it somehow automatically figures out how to start, Catoni's algorithm threw out elements according to this influence function, where it needed to know sigma in order to figure out what to throw out. Instead, we're saying the clean answer is throw out a third log delta elements. So it's a much cleaner answer about how to throw out outliers, and it yields these results without having to know the width of the distribution. Okay. Okay, so I have very little time, but I want to. Okay, well, yeah. Instance optimal extensions, things like that. I want to tell you just a tiny bit about high dimensions. So mean estimation, and the thing which I promised at the beginning, tail bounds. So tail bounds, we have this intuition that the sum of independent bounded random variables behaves somewhat like a Gaussian. And in one dimension, we're familiar with lots of these things. And I want to tell you about a high dimensional version of this. So one of the really crucial things for anyone who starts thinking about high dimensional Gaussians, there's a really big intuition if you haven't seen this before, is that high dimensional Gaussians behave like spherical shells. So I want to convey this diagram to you. This is crucial. So take samples from a d-dimensional Gaussian and normalize by 1/√d just for the sake of drawing things. So if d equals 1, then the radius of a sample looks roughly just like half the Gaussian. Okay, nothing interesting there. As d increases, it moves away from 0. But for higher and higher d, the radius adheres more and more closely to a spherical shell. Okay, so for very high dimensions, a sample from a Gaussian looks really similar to a sample from just a sphere. Not a ball, but a sphere. Okay, the issue is that if you look up tail bounds for sums of independent random vectors, previous tail bounds don't have this behavior of adhering more and more tightly to a spherical shell in higher dimensions. Somehow previous tail bounds, like matrix Chernoff bounds, for example, have the same behavior for every dimension. Somehow the tail here somehow fits all of the different dimensional cases instead of improving its tightness as the dimension increases. So here we're going to have a band that actually adheres more and more tightly to a spherical shell with higher dimension. So, okay, to try and end this talk very soon. So again, the result says for a general bounded distribution, even when the distribution itself doesn't look like a sphere, the sum of many samples does. Okay, so I'm gonna skip some stuff here. Prior work. So this is all fairly recent work. So this problem in high dimensions was only really tackled fairly recently, which shows that it's a very challenging problem for high dimensions. This work, which I'm not going to be able to explain except just in 1 minute, does not subsume this previous work, but just looks at the special case of high dimensional distributions. Well, high dimensions is defined as the dimension, the effective dimension of the covariance matrix is bigger than the square of the logarithm of delta of the desired confidence. So there's some condition here. But under this condition, things get vastly simple. Instead of exponential time algorithms or things like that, instead of a constant of 480,000 squared in the sample complexity, everything will be linear time, 1 plus little of 1 optimal, and extremely simple, but assuming high dimensions. Okay. The tail bound here is a vector extension of the Bernstein bound. The Bernstein bound shows that sums of IID samples from a one-dimensional bounded distribution, where you've got some variance sigma and some radius r, then it's got some tail bound with some sigma dependence and some r dependence here. And we generalize this to something that looks very similar, where the probability of being t more than the spherical shell of appropriate radius, depending on the trace of the covariance, has a very similar dependence on as the one-dimensional bound. And to just briefly try and explain the punchline, so sums of bounded random variables behave like they're bounded with extremely high probability. So the algorithm is as simple as you can imagine. Throw out everything that's too far away from the center. Thus, once we've thrown everything out that's too far, we have samples from a bounded distribution. Therefore, everything behaves like a Gaussian, and then return the mean of what remains. So we leverage this heavy-duty new vector Bernstein bound to come up with a ridiculously simple algorithm that just says, throw out the far away things, return the mean of what remains. linear time, very simple analysis, very flexible, doesn't depend very sharply on delta. And yeah, that's it. Okay, thanks.
Questions for Paul?
So your sample complexity naturally depends on delta. Is it obvious that, so for a specific delta, you need some number of samples. Is it obvious that for any delta bigger than that, you, because your algorithm also perturbs the sampling process based on the delta value? Does that hurt you when delta is bigger? Let's say you don't know exactly what delta you're aiming for, you just have a lower bound?
Okay, so I skipped exactly describing the theorem in the high-dimensional case. So are you asking about once we throw out samples, then the samples that remain are dependent on?
Just tilting the shape of the distribution, the shift that you had was a function of delta,
Right.
for example. So for example, the number of outliers that you throw away is a function of delta, right?
Right. So if you throw out too few things, then you'll have a lot of outliers and you won't be robust. If you throw out too many things, then the stuff you've thrown out may shift the mean. So you need to choose the right balance between throwing out enough things that the vector Bernstein band applies, but not throwing out too many things that the stuff you throw out will contribute enough to the mean that ignoring it is dangerous.
Okay.
Yeah, so you'll end up throwing out roughly 1 over, sorry, the square of the logarithm of 1 over delta things. So again, in the one-dimensional case, we threw out 1/3 log delta outliers. In the high-dimensional case, we're throwing out log squared 1 over delta outliers. This is some sign that these two algorithms are incomparable.
Okay, thank you.
Any other questions? Okay, so for the interest of time, let's take the break and let's thank Paul again.
Thank you.